Hello everyone, and best wishes for your safety and health during this pandemic. So my name is Wan Muhammad Haziq, and I would like to present my final year project. So my final year project title is a design optimization of a C-loop intraocular lens using designs of experiment. And my supervisor name is Dr. Nafawazi bin Nuruddin. So first, let's look is a my project objective. First is to study the main design parameter that affect mechanical stability of an intraocular lens. Second is to explore the effect of compression force, axial displacement, tilt, and rotation. And last but not least is to be able to get an optimum shape of intraocular lens. And later, in the following slide, we will be able to see if I have completed all of the objectives stated or not. So, for the method, there are two methods for gathering data for my project, which is design of experiment and using a finite element analysis. Both of these which will be discussed briefly in the following slide. But first, let's take a look on what is IOL and what is meaning of IOL. So basically, IOL is an intraocular lens. It is a small artificial lens that is implanted in the eye. It replaces the natural lens of the eye, which is removed during surgery. The question is, when will we use the IOL? So, IOL is mostly used as a part of treatment for cataract or myopia. The advantages of IOL are that they can improve vision and can correct for nearsightedness, farsightedness, and astigmatism. So, for the biomechanical stability, for the biomechanical stability of the IOL, this is what we need to measure in order to improve its efficiency. Biomechanical stability can be evaluated through four main parameters, which is compression force, also known as a reaction force, axial displacement, tilt, and rotation. These are the factors that will determine IOL efficacy. There are also a few influential factors in the post-operative stability of IOL that will affect the biomechanical stability of IOL, which is material properties, haptic design, and size of the IOL, which some of them already have a standard procedure and measurement. A haptic design is one of the main changing variables in my project. So what is haptic? Basically, haptic is a small filament connected to the optic, and its function is to hold the lens in the place in the eye. To study the effect of the haptic design on the biomechanical stability, 16 geometrical variations were created according to the methodology of design. According to the methodology of design of experiment, we use a finite element analysis by Abaqus software, which is Abaqus 6.14, to evaluate the biomechanical stability of IOL with a different haptic design following the procedure described in ISO 119793. So basically, Abaqus FEA is a software suite for finite element analysis and computer-aided engineering. The reason we choose Abaqus because it allows for more variety in mesh element types, as well as finer control of defining connectors. We use a standardized procedure to approximate the behavior of the IOL in the capsular bag, which is ISO standard 119793. In this compression test, the IOL is placed between two clamps with a curvature radius of 5 mm and compressed to measure its mechanical stability. The clams are initially separated a distance equal to the overall dimension of the IOL to allow its gentle positioning without introducing pretension. The right clamp is displaced until a compression diameter of 10 mm while the left clamp remains fixed. The compression or reaction force at the horizontal plane was reported only at the end of the compression. The axial displacement, tilt, and the rotation were evaluated by comparing the initial and final configuration of the lens following the standard ISO, which established that 4 key points must be recorded in order to determine the stability of the IOL. For the variation of the haptic, we use a Minitab software to do a full factorial design using design of experiment. So basically, Minitab software is a statistical analysis software that can automate calculation and the creation of graph, allowing the user to focus more on the analysis of data and the interpretation of result. We will get 16 different variation of haptic design from the factorial design based on the parameters we set. What makes it more exciting is that we improvise. Our final project is improvised by adding one new parameter aside from the standard reference paper to have more precise data. Basically, we have an angle HC and J that were the main parameters at the haptic, with a radius as a secondary parameter that we have added. After all of the simulation have been completed, the recorded data will be organized and some of the data will be entered into a Minitab to get an automated graph and calculation result. This is the graph result from Minitab. So for the result and the conclusion, this is the graph result from Minitab, which is a Pareto chart of effect. It determines which parameter have the most influence on the biomechanical stability of IOL. As we can see that the angle and the radius are the most important factor in determining reaction force and axial displacement. We also have ANOVA, or called as analysis of variance, for each properties to check the impact and the influence of some parameters to the haptic. This is the entire displayed data graph with axial displacement, tilt, and reaction force. For 16 design, included is the highest and lowest point of regarding to the data measured. From the graph, we may discover the lowest point of reaction force, axial displacement, and tilt. As the design may alter from graph to graph. For the reaction force graph, design 14 has the lowest reaction force, and for the axial displacement graph, you can see that design 7 has the lowest axial displacement. And for the tilt graph, we can see that design number 1 has the lowest one for the tilt. We can conclude that the ideal shape may be the lowest of all biomechanical parameters, as in some reference study, they select the lowest response force, known as compression force, as the ideal design of the IOL. So in this project, design 14 is the best form since we only consider the lowest reaction force of all design, and we already know which parameter will have the greatest influence on biomechanical stability. Finally, after devising the optimal design, we were able to effectively meet all 3 of the previously stated objectives throughout this final year project. Thank you for watching. That's all from me.